Chapter 17, the Earth's atmosphere. Why is our atmosphere important? First, because it protects us. It protects us from the UV rays. The Earth's ozone layer is located at the top of the stratosphere, and it reflects most of the ultraviolet radiation from the sun. Too much UV radiation from the sun can cause skin cancer. Our atmosphere also protects us from space debris, like meteors that normally burn up in the mesosphere. Sometimes we call those shooting stars. So when you think you see a shooting star, you're actually just seeing space, dust, and trash burning up as it enters our atmosphere. But it's still pretty. It also traps heat. The greenhouse gases, such as carbon dioxide, methane, and water, help to trap heat near the Earth's surface. That's what makes it livable. It also gives us air to breathe. The air that you're breathing, though, is only about 21% oxygen. Throughout the history of the Earth, we can tell from different sources that the concentration of oxygen on Earth has fluctuated. It's gone up, it's gone down, but it's roughly stayed around that 20% mark. It also provides us with weather. Earth is the only planet to have water in all the phases, solid, liquid, and gas. Only within the troposphere does the water cycle occur. Chapter 17.1 is over the composition of the Earth's atmosphere. The atmosphere is composed of a mixture of invisible gases extending from the surface to an indefinite height. The upper limit is hard to mark because the gravitational pull becomes very weak the farther you are from the Earth's surface, and the molecules are slowly drifting out to space, much like your attention spans. 300 miles above sea level is commonly the maximum upper limit. The three major components of our atmosphere include dry gases, water vapor, and solids. The main gases include nitrogen, oxygen, argon, carbon dioxide, ozone, water, and solid particles. Nitrogen, carbon dioxide, oxygen, and argon make up 99.9% volume of dry air. Nitrogen and oxygen make up 99.03% of that volume. The primary concern of meteorologists is the lower 30 miles, which includes the troposphere and the stratosphere, and that makes up 99% of the entire mass of our atmosphere. If we were to shrink the Earth down to the size of a beach ball, like the one hanging on the ceiling in the classroom, the inhabitable atmosphere would be roughly the thickness of a tissue paper wrapped around it. The gases that make up our atmosphere include nitrogen, which is tasteless, odorless gas. It makes up 78% of the volume of air. There are bacteria that convert gaseous nitrogen into nitrite compounds. Small amounts of nitrogen compounds are converted in thunderstorms. So you may hear farmers, old-timers, talk about how it's good that the thunderstorms are bringing rain, because they bring more than just moisture. They're also bringing some of those nitrogen compounds to the Earth. The second gas is oxygen. O2 is tasteless, odorless, and colorless, and it makes up 21% of the volume of air. It's highly reactive and it combines with almost every other element. One of the common things we see it reacting with is iron. It creates iron oxide, commonly known as rust. It's necessary for the life of animals and for plants. Sulfur, that's released naturally throughout wherever in the world, will combine with this to form SO2, or sulfur dioxide. When it combines with moisture in the air, it creates sulfuric acid, or acid rain. Another source that you can see that is with onions. When you chop up an onion, they have a high concentration of sulfur in them, and it releases that sulfur. It combines with the oxygen in the air, which is why it only happens when you cut them. And that sulfur dioxide, as it's rising up from the onion, will hit your eyeballs, and it starts to irritate them. And then it mixes with the moisture in your eyes, and it creates essentially sulfuric acid. And that's why your eyes water and you cry when you cut onions, because your eyes are trying to flush that sulfuric acid out. The third gas is argon. It's inert, meaning it doesn't react. It's mainly used in welding and electronics components. The fourth gas is carbon dioxide, colorless, odorless gas with a sour taste when lots of it's mixed with water. So think about when you go to the gas station, and if the flavored syrup runs out and you just get that clear, bubbly water and you take a big old drink of it, and it's just super, super bitter. That's because that's just carbon dioxide and water. Okay? Photosynthesis is the most important part of the carbon dioxide cycle. It can change from a solid to a gas, so that dry ice doesn't leave puddles behind. CO2 is a major pollutant of our atmosphere. So it's kind of a double-edged sword there, because we need it, but it's also a pollutant. It prevents radiation that's emitted by Earth from escaping into space, but too much of it can result in global warming. Now the kicker with that is global warming has always been going on. The Earth throughout its entire history has been on a constant cycle of heating up, cooling down, heating up, cooling down. Right now we're in one of those warming phases. Eventually it will start cooling back off and we'll enter another little ice age. Human beings are not creating this. This would go on even if we weren't here. But human beings do things that will contribute to the speed that that's happening. So if you don't believe it's real, there's obvious places we can see pictures, like in 1928 in Alaska. It's definitely happening. That ice glacier has melted and it's now full of a lake. Next we have ozone. O3, it's a bluish tinged gas with a pungent garlic smell. It's considered rare but essential. You can find it at altitudes of 12 to 18 miles, and its job is to filter out UV rays. Chlorofluorocarbons, or CFCs, from aerosols and refrigeration can break down O3. Chemical fertilizers can add nitrous oxides that will disrupt the creation of ozone. On the surface, though, here down where we're at, it is one of the most powerful pollutants. It's made by burning fossil fuels and a little bit by lightning. It can destroy rubber products, cause lung damage and eye irritation, and it can damage crops and forests. Next we have water. It's a pale blue odorless liquid which, including that trapped as ice and ice caps and glaciers, will cover about 74% of the Earth. Which is kind of neat because you think 74% of the Earth is roughly water, roughly 75% of your body is water, 75% of your cells is water, so that's one of those emergent properties we talked about in biology. 90% of all the water vapor that's found in the atmosphere is located within 2 to 3 miles of sea level. Number 7, the solid particles. These are a suspension of small liquid or solid particles in a gas. Major sources include sea salt, which happens when the waves crash along the shore. It creates sea spray, which puts the sea salt into the air. There's wind-blown dust, forest fire debris, and volcanoes. Those forest fires and volcanoes can actually carry, the wind can carry that debris hundreds of thousands of miles. Man-made sources, including burning of fossil fuels in agriculture, also contribute to solid particles. Finally, the cloud condensation nuclei. Many aerosols act as centers on which condensation of water vapor takes place. Cloud seeding is a process that they started back in the 30s during the Dust Bowl days. They started aerosolizing silver nitrate and using planes to spread it. And it's a good idea because you're putting those nuclei into the atmosphere and it's going to create clouds. But the problem is it's not predictable where those clouds are going to end up raining at. 17.1, the height and the structure of the atmosphere. The vertical structure of the atmosphere starts with the troposphere. The Greek word topo means to turn, and it's characterized on average by a decrease in temperature with height. So as you go up, it gets colder, just like climbing a mountain. The average thickness is about 7 miles. So the troposphere starts at Earth's surface and goes up roughly 7 miles. But if you're at the equator, it can extend to 11. And if you're at the pole, it can go only to 5 miles. And that's because the Earth itself is not a perfectly round sphere. The troposphere contains about 75% of the total mass of the atmosphere, mostly all the water vapor and the solid particles. This is where all of our weather occurs. The overturning of air occurs here, and that's what distributes heat, moisture, and solid particle matter. Next, we have the stratosphere right on top of it. The Greek strato means horizontally layered. The temperature is nearly constant in the lower portion, and it increases with height. The average height extends from 7 to 28 miles. The vertical motion and overturning are greatly reduced here, so there's not much wind, there's not much motion there. The stratosphere acts like a giant lid on the overturning troposphere. So all of that weather that's occurring in the troposphere, it would bubble up much like a pot of water would bubble up on the stove if you were boiling it. But we put a lid on it, or the stratosphere, and it kind of contains it. Every once in a while, you get a system that has more energy in it, and it will actually burst through and it will enter the stratosphere. When that happens, we have those big, giant, towering cumulus clouds that will actually stay aloft for a very long time. So the temperature inversion that happens here results in a minute amount of water vapor that's being put into the stratosphere by those giant thunderstorm clouds. And there's also a lack of dust and solid particles up there. The only thing that gets up there is occasionally volcanoes will shoot high enough. They can put some dust and solid particles. And those particles will stay suspended for years because they're just far enough away that gravity doesn't affect them, and there's no wind or condensation to pull it back down to the Earth. So there's few clouds and no precipitation at that level. So that's ideal for planes, the big jet planes. They want to fly in that level. Most of our ozone is found here. There's a maximum concentration found at about 15 miles above Earth's surface. So in Las Vegas, obviously, there's a stratosphere because it's the tallest tower. Here in the diagram, you've got the stratosphere right above the troposphere. Notice there's no clouds up here, but we do have jet planes, weather balloons. There's other things up there. The mesosphere is the next. The Greek word meso means middle. It's characterized by sharply declining temps reaching negative 93 degrees Celsius at the top. The height lies between 27 and 55 miles above Earth's surface. And then thermosphere. The Greek word thermi means heat. It begins at 55 miles and extends to the outer edge of the atmosphere. It's characterized by high temperatures due to thin air. The estimated temperature is as high as 1,370 degrees Celsius, but because of the very cold air, or very thin air, the lack of molecular movement makes it feel much colder. So much like if we had 1 or 2 hyper kids in the classroom, it wouldn't seem like it's that bad. It wouldn't be that loud and rambunctious. But if we had all 20 of the rambunctious kids in one classroom, it would seem much more chaotic. Same thing. If we have very few particles, the temperature could be very high, but those molecules may be moving very fast, but they're very spread out, so it doesn't feel warm. Aurora borealis and aurora australis occur in the atmosphere. So these are the northern lights and the southern lights. And they are just the result of showers of charged particles being thrown from the sun into our upper atmosphere during solar magnetic storms. So that's what gives us the pretty colors. We also have these zones of transition. These are regions where different layers of the atmosphere interact. Usually they're roughly about a mile thick, and we call them pauses. So between the troposphere and the stratosphere, we find the tropopause. Between the stratosphere and the mesosphere, we find the stratopause. See how this is going. The ionosphere and ozonosphere. The ionosphere is a minor layer and it's located above the thermosphere. Unfiltered X-rays and UV energy from the sun ionize gases. These charged atom ions will interfere with shortwave radio transmission. Radio waves above 30 megahertz will normally pass through this layer, where frequencies below that are bounced back to the Earth, resulting in long-range communications. The ozonosphere extends from the bottom of the stratosphere to about 30 miles. All the ozone in the upper atmosphere is found within this region. If all the ozone here was compressed and brought back down to sea level, we would end up with a layer only a fraction of an inch thick. The harmful UV energy, most but not all, is filtered out here. So the vernal equinox is also known as the spring equinox. On the equinoxes, the sun shines directly on the equator, and the length of day and night are almost equal. This marks the moment the sun crosses the celestial equator. In 2020, this happened on March 19th. This date does actually change from year to year. The summer solstice is the longest day of the year and is the start of the summer season. Technically, it occurs when the sun is directly over the Tropic of Cancer. In 2020, it happened June 20th. The autumnal equinox, or fall equinox, officially marks the beginning of autumn in the northern hemisphere and spring in the southern. This past year in 2020, it happened on September 22nd, and again, these dates change from year to year, so be sure and look those up. The winter solstice is the shortest day of the year and the longest night. It's when the sun in our sky's dome reaches its farthest southward point for the year. After that point, the days slowly start becoming longer and longer. An isotherm is just a line on a map, that connects points having the same temperature at a given time or on average over a given period. A lot of times you've seen maps that look like this. You just may not realize it. The Earth's orbit and seasons. The Earth orbits the Sun once every 365.25 days. It follows an elliptical orbit. The Earth is closest to the Sun in the northern hemisphere during winter and farther in the summer. Our seasons are regulated by how much incoming solar radiation reaches the surface, and that amount is determined by the angle of the Sun and the length of the daylight. How close we are to the Sun matters far less than those two things. So if we were to look at this diagram of the flashlights on a grid, you can see that the higher the Sun angle, the more direct radiation we have over a smaller area. If we have this flashlight here at an angle, it's going to cover more area, but there's also going to be less radiation in one direct spot. So less atmosphere means less scattering and absorption by air molecules. You may have heard the saying, red sky in morning, sailors take warning, red sky at night, sailors delight. That saying comes from the fact that in the morning, when the Sun is coming up and it's passing through all the atmosphere, if there is a lot of moisture, that will set us up for a series of possible storms, possible rain during the day, which would be obviously bad for sailors. If it happens at night, it's not so bad because then all of that incoming radiation goes away for the night and gives things a chance to cool down. The moisture can precipitate out or fall out of the sky and settle. That's also why we have such beautiful sunrises and sunsets, is because of the amount of moisture in the air. So the length of day, the longer the daylight hours, it just means we have more energy available from the Sun. It provides more opportunity for warmth. So in the summertime, we have a little over 14 hours of daylight. In the wintertime, we have less than 8. We just have less energy available from the Sun. In the northern hemisphere where we're at, the astronomical summer begins June 20th. And again, remember, these dates will change. The summer solstice, the Sun's rays are the most direct. The days are very long, and the Sun is high in the sky all day. The astronomical fall begins on September 20th. This is also the time when the Sun starts getting lower in the sky, the days start getting shorter, the direct rays across the equator. And in the vernal equinox here, which is the spring equinox, the exact opposite happens in March. So the Sun starts getting a little bit higher in the sky, our days get longer, and we have fewer direct rays right across the equator.